Okay, good afternoon, everyone. This is lecture 13, and we're going to talk about two important reactions in this in today's lecture. We'll talk about hydroboration oxidation. So this is a very reliable method to take an alkene to the less substituted alcohol, and then we'll talk about oxidative cleavage of alkenes by ozonolysis, and that's a again, very reliable way to take an alkene, in this instance, to a carbonyl compound. So start with hydroboration. So I'll write out the general transformation, and then we'll go through the mechanism. And so this is a two-step process. So in the initial step, we're going to start with our alkene. And we're going to use 3 equivalents of that to balance the equation. So you'll see in a second why. So 3 equivalents of alkene plus 1 equivalent of this molecule, which is borane tetrahydrofuran complex. Okay. These react to form an intermediate that we refer to as a trialkyl borane. So okay, so you can see that I've incorporated three equivalents of the alkene into the boron center, and hence that's the basis for the stoichiometry. And so this is a trialkyl borane. Okay. If we followed the hydrogens on the borane, what we would find is that they end up 2 carbons away from boron. So let me draw in, color them blue here, BH3, and then you end up with an H here, an H here, and an H here. Okay, and then just to avoid any confusion, there is of course a hydrogen that comes in with starting material that is also attached to that same carbon. Okay, so the boron ends up attached to the less substituted carbon of the alkene. Okay, and that has important implications for the structure of the alcohol that's produced. And so in step 1, you treat the alkene with a borane complex. Here we use borane tetrahydrofuran complex. Step 2 is going to be an oxidation, where you'll treat with sodium hydroxide and hydrogen peroxide. Okay. And what comes out of that reaction then is the alcohol okay, where that hydroxyl group is derived from the sodium hydroxide, okay? And so if I number carbons in the substrate, so let's call this 1 and 2, we have 1 and 2 and 1 and 2. So the boron attaches to position 1, the less hindered carbon. And then the alcohol substitutes boron at the same carbon. So the alcohol ends up attaching to the less hindered carbon atom in the product. So, or less hindered carbon atom in the alkene. Or let me just rewrite hydroxyl. Okay. And so this is a 2-step process. Again, as we did with oxymercuration reduction, we can write this in a condensed form. Okay, like that. So putting all of the reagents over a single arrow. Okay. So next we'll talk about mechanism. And to discuss the mechanism of this reaction, you need to understand the hybridization and bonding in boron. And so the boron center has 3 ligands on it. And an empty 2p orbital. And so this is BH3. Okay. It's trigonal planar, and the 2p orbital is empty. Okay. Borane is a gas itself, and it actually forms a dimer known as diborane. We prefer to work with reagents that are non-gaseous, and so that's why we use the THF complex. The THF complex is essentially the product of an acid-base reaction between the boron and the tetrahydrofuran. So okay, and so BH3THF is a nice liquid. You can syringe it and handle it, right? The boron in the complex has 8 electrons. Okay. In the free borane, it has 6 electrons. Okay. And for interaction with an alkene, we're going to require that empty 2p orbital. And so there's an on-off rate of the tetrahydrofuran with the borane, and we assume that reaction occurs through free borane. Okay. And so let me go to the next slide and we'll draw out the mechanism. So I'm going to invoke just BH3 for the reasons I just discussed. Okay. And when the borane approaches the alkene, you're going to form what we call a 4-center transition state. So I'm going to draw that here. So okay, and I put double dagger up there to indicate that this is the transition state structure. So this is the top of the reaction energy diagram. And in the transition state, you're forming CH, CB bonds and breaking the pi bond and the BH bond, okay? And so the initial product then of that reaction is going to be what we call monoalkyl borane. So I've added that BH to the internal position of the alkene. Boron's attached to the less substituted position. Okay, so mono. And because this is a 4-centered transition state, there's actually, there's sort of quite a bit of molecular organization that needs to occur for the reaction, for the addition to proceed. And for that reason, the reaction is very sensitive to steric effects, to non-bonded effects. And so because the boron is bigger than hydrogen, it's easier for it to attach to the terminal carbon. The other mode of addition, so let me explicitly draw it. Okay, this is disfavored due to sterics. All right, so now I got the boron coming into the carbon that's more substituted. There's more steric encumbrance. It's harder to actually do that reaction. And so in these hydroborations, the reason these are so useful is that boron reliably ends up on the less substituted carbon. Okay. And so you first form a monoalkyl borane, and then there's still 2 BH bonds left in our molecule. And those can then react in the same exact way with 2 more equivalents of the olefin. So okay, and that's how you get to that trialkyl borane intermediate. Okay. All right, so that is step 1. So treat the alkene with borane, do this hydroboration reaction where the boron attaches to the less substituted carbon. Do it 3 times, 3 equivalents of alkene, get to your trialkyl borane. You form that in solution. And then the second step, you're going to add the sodium hydroxide and hydrogen peroxide. Okay. And to consider what's happening, we first need to remember the pKa's of hydrogen peroxide and water. Okay. And so So the pK of hydrogen peroxide is about 11 and water is 15.7, right? And so what that means is that when you add hydrogen peroxide to sodium hydroxide, when you mix them, you get proton transfer from the hydrogen peroxide to the hydroxide to form water. And this species on the right, which is known as superoxide anion. Okay, and the superoxide is what's going to be our reactive, our reagent for the oxidation of the borane. So you have your trialkyl borane in solution. Let me redraw it. Okay, and remember, we're back to 3-coordinate boron. So this is trigonal planar, and there's going to be an empty 2p orbital on boron. Okay, and so if I want to show that explicitly, I can draw my trialkyl borane with stereochemistry. So this should be a carbon there. So screw this up. Let's redraw this thing here. And then I've got my empty 2p orbital. Okay, and so what's going to happen is that superoxide anion that's in solution is going to attack that 2p orbital. And when I do that, I'm going to form what we refer to as a borate. So a borate is boron with a negative charge. Okay, and so right, and then there's a very interesting step that occurs, which is a 1-2 migration of the alkyl substituent. So we're going to take the electrons in the carbon boron bond, and you can do this for any of the alkyl groups. They're all equivalent. So we're going to take those and push them over to oxygen. Okay. That oxygen currently has an octet. And so to avoid violating the octet rule, I have to break a bond. And the bond I break is the OO bond. The reason I can do that is that OO bond is actually very weak. So typically about 36 kcals per mole. That's less than half the strength of a normal sigma bond. So it's very weak. And what that serves to do is make a stronger CO bond. It relieves the negative charge on boron. So now that negative charge is on hydroxide, and I form my first intermediate. I'm back to a trialkyl borane. Okay, except that I've substituted one of the carbons bound to boron now with oxygen, right? And so just like in the first hydroboration, that oxidation is going to repeat twice, and I'm going to oxidize the remaining 2 alkyl ligands on boron. So let me draw that here. Okay, and then that intermediate is known as a borate ester. Okay, and so that essentially has my alcohol product. It's just attached to boron. And so to get it off, there's water in solution. That water is going to exchange with one of the alcohols, or with all three of them. So I'll show it for one. You can imagine water coming in and attacking the now empty 2p orbital on boron. Okay, I need to balance my charges, and so boron's negative, the oxygen is positive, and then there's a proton transfer. So we can take the electrons in the BO bond, have them attack that hydrogen, and then push electrons down to oxygen. And what you end up with is the free alcohol, plus now you have hydroxide attached to the boron. Okay, and as before, we can repeat this 2 more times. And ultimately, we end up with 3 equivalents of our alcohol plus BOH3, which is boric acid. And boric acid is what they put in, ant repellent and things, okay? And so this reaction's a bit new in the sense that we haven't seen these 4-center transition states yet. And there's kind of this unusual stoichiometry issue where you're getting 3 equivalents of product for each borane that you put in. And also the key to the success of all of this is making use of that empty 2p orbital on boron. So those are kind of the 3 things that you want to make sure that you're solid in terms of your understanding, the sort of the role that the 2p on boron plays in this transformation, the fact that you can get 3 equivalents or 3 hydroborations, and then this unusual sort of 4-center transition state. All right. And so hydroboration takes alkene to less substituted alcohol. I want to conclude this part of the lecture by just summarizing the ways that we learned thus far to take alkenes to alcohols. So okay, so let's start with our generic alkene. This is called tert-butyl-ethylene, for those of you that are curious. Okay, and so we know 3 reaction conditions. So one condition is sulfuric acid, water, right? The second conditions that we learned are mercury trifluoroacetate, water, and then sodium borohydride, NaOH, right? Maybe let me just redraw this because these are 2-step reactions. So we'll call this one A, method B, step 1, step 2, and then method C now is BH3, THF, step 1, step 2, NaOH, H2O2, okay? Okay, and each of these conditions gives a unique product. And so what I'd like you to do is work through those as a review and sort of a summary here. Work through these conditions on your own. if you go through the mechanism, see if you can arrive at the right product, okay? And then, you can check this against what's in the text in your earlier notes. But these methods are inequivalent in terms of their outcome. In all cases, we formally add the equivalents of water across the alkene, but the products that form are different. And that's why we learn the different methods, because you can get to different things from the same starting material. All right, so I'll stop there, and we'll do the second half of the lecture, which will be a discussion of ozonolysis.